So we can get started. Before we get back to the talks, I just want to remind you that tonight is our public lecture. So every year at TASI there's one public lecture which is sort of given on a level to the general public. Nadi Seiberg is giving a public lecture this year. It's called The Frontiers of Fundamental Physics. So if you'd like to attend, it's at 7:30 p.m. tonight. And it's just downstairs, G1B30, one of the big lecture halls, just one floor below where we are. So with that said, we'll return to our discussion of anomalies and topological theories in relativistic.
Thank you. So I'd like to continue our discussions from yesterday. So I'd like to continue talking about the anomaly of the fermion and the Ada invariant. So yesterday we considered a very simple case of fermion on a one-dimensional line and computed the Ada invariant very explicitly. So today let's start by thinking a system which is a bit more complicated. So let's say we want to discuss the anomaly of 2D complex chiral fermion. So let's say you have that on some 2D space, right? Well, I should write it more as a closed manifold. So you have some 2 manifold Y2. And as we discussed yesterday, its anomaly is captured by considering something in 1 dimension higher. So this is what W3. And here, as we discussed yesterday, you consider partition function of a massive fermion with very large mass divided by the same thing with very small mass. So by combining the boundary massless complex fermion with this ratio of the partition function of massive fermions, things become well defined. But the price we need to pay for this property is that it depends. The value depends on the way you extend it. So given the same Y2, you can choose a different extension, W3 prime, and you can consider the same thing. So this has a definite value. This thing also has a definite value, but these two things usually have different values. So you can consider their ratio. So you can consider their ratio. The ratio is just the same Z fermion with very big mass divided by Z fermion with very small mass evaluated on the combination of 2 manifolds, W3, this one, and the orientation reversal of the other thing. So you just evaluate. You just need to evaluate this thing. And this is, as I said, is the definition of something mathematicians call the Ada invariant. So in order to characterize, or in order to understand the anomaly of 2D complex fermion, you would like to understand this Ada invariant. And because this is just a free theory, you have a formal, very general expression saying that this is just equal to, you have a formal formula saying that this is just 1/2 sum over all of the Dirac eigenvalues of the Dirac operator, and you sum over the signs. So that's it. Excuse me. So we can continue discussing the physics, but I'd like to spend the first 15 minutes or so to tell you to go through a rather technical computation, just to show you that Ada invariant is something you can compute. I mean, because I have my personal experience of having a lot of fear into this Ada invariant. I mean, it just looks very abstract. Right? You have a formal formula, but how do we evaluate it? So I just want to give you an example where you can actually compute it, right? So this will be just a technical mathematical computation for about 15 minutes, I guess. But I think this might have some good psychological effect to you. Maybe it gives you a bad psychological effect, but we'll see. So we would like to consider the case when W is just S3 over Zn. So this is called length space, nothing special. The reason why I choose this quotient is that if you just use S3, it turns out to be 0. But so this is, you know, S3 is a group manifold of SU2, right? And it has an action of SU to L and SU to R. So you have an action from the left, from the right. And let's say that this Zn acts via an element in this SU to R, which is x inverse, where x to the nth is 1. So you take this element, right? And you take the quotient. And that's the length space you have. So you need to know the Dirac eigenmodes on this length space, right? But for this purpose, of course, it's enough to know the Dirac eigenmodes before the quotient and to know how this element acts on these Dirac modes, right? So the trick of the computation is the following. So instead of considering the Ada invariant of the length space itself, you consider the Ada invariant of S3, but with a weight factor x, which I define to be the summation over the Dirac eigenvalues, but you weight the sign factor by this element, right? Because this x is a generator of Zn, and it acts on S3. Therefore, it acts on all of the modes. So each mode has a definite way of transforming under this Zn. So I'm calling it as 2j. J is just a standard eigenvalue for this SU to R. And I'm weighting each sign using this eigenvalue, right? So from this, you can easily compute. If you know this, you can easily compute the original Ada invariant we are interested as follows. But first, I need to explain to you what is this additional parameter omega. So omega is a complex number which is the nth root of unity. And the reason why you can choose it is that because you quotiented S3 by Zn, of course, pi 1 of S3 over Zn is Zn itself, right? So therefore, if you consider fermions on S3 over Zn, you need to choose, specify the holonomy of the fermions around this circle, right, generating this Zn. So that's specified by a phase you get if you go around it, and because it's just a Zn cycle, if you go around it n times, it cannot receive any phase. Therefore, the phase you can have is this omega, which is an nth root of unity. So this means that, in other words, this means that you need to keep only those modes on S3 such that, I mean, X, suppose you take X to be just a standard generator, and if you take 2j's power of it, this equals omega, right? I mean, depending on the holonomy you want to have, you just keep the moles on S3 before the quotient, which has exactly the holonomy you want. So this means that this term, this Ada invariant on the quotient, is obtained by keeping only those terms in this sum where this part happens to be equal to, happens to be specified with this omega. So you can easily see that this eta omega is just the sum over all possible k from k equals 1 to n, and omega to omega inverse k, and eta S3 x equal exponential 2 pi I over n. So it's just, I'm just using, in some sense, the discrete Fourier transformation to project that sum onto the term you want to keep, right? So in order to compute the Ada invariant on the quotient, you just have to compute this weighted Ada invariant of the original three sphere. So how does it work? Well, so the problem was reduced to know the Dirac spectrum on S3. So you have S3, and you have a spinor bundle on top of it, right? And you'd like to know how the spinor bundle decomposes under the eigenstates of the Dirac operator. So you have the sections of the spinor bundle, right? And of course, there's an action of SU2 times SU2L times SU2R, right? So you can decompose this space under this representation. So I'm just doing the analysis of the spherical harmonics, not on S2, but on S3, but in the spinor representation. So I'm not going into the detail, but the result is that you just get the sum over the following pieces. I will explain the notation. So when I write the tensor product, this side is for SU to L, and the other side is for SU to R. Similarly for this, and this VD is just a d-dimensional E-rep of SU2. And so this is the standard decomposition. And you know that on the round S3, the Dirac operator has the eigenvalue d plus 1/2 here, and the eigenvalues minus d plus 1/2 there, right? So it's very explicit. So you learned that, I mean, all we have to do is to compute this, right? And we know all of the eigenvalues very explicitly, and you can easily compute the signs. So this side, the sign is positive. The other side, everything is negative. And therefore, eta of S3 weighted by x is just 1/2. And I put the exponential regularization just to have some, to be easier. And as I set up the problem, this Zn quotient x only acts on this SU2R part, right? So the SU2L part just appears with the multiplicative factor, and you just need to take the character of SU2 for this d plus 1 dimensional representation on this side. And because the sign is positive, you just multiply by plus, right? And there's a similar contribution, d plus 1, I guess, and chi d of x. And you have a minus sign because the eigenvalues are all negative. And of course, this diverges if you don't do anything. So I would put the convergence factor weighted by the Dirac eigenvalue itself, right? And I forgot to include the sum over V. So again, this is an extremely simple sum. Thanks, I mean, this is just exponential sum together dressed by some quadratic polynomial. And it's extremely easy to take the s goes to the 0 limit. So it's just it just happens to be this very simple number, right? So with this you can compute the Ada invariant of the length space very explicitly. So for example, Ada invariant of S3 over Z2, so this is just the Z2 quotient, and there are two choices. Omega can be either 1 or -1, right? And in this formula, you can just plug it in, and you find that you have -1/8 here, and you have this +1/8 here. So that's the result. So pretty simple, but you get some explicit result. I need to tell you one thing, that here I started by considering complex chiral fermion, right? But in 2D, of course, you can also consider Majorana fermion. In that case, you need to use real fermion on the 3D space too. This means that only you need to keep only half of the eigenvalues. So in the end, you need to divide by 2. So this is for Dirac fermion. I mean, yeah. But for the Majorana fermion, well, Dirac is a bad word. I mean, complex fermion. But for the Majorana fermion, what you get is instead minus 1/16 and plus 1/16. So that's some explicit computations you can do. So yeah. Yes. Just on the left. You're right. So I'm sorry. Yeah, Majorana Y. Yes. Right. Thank you. So I just wanted to. I just wanted you to know that these things are computable. Right.
Could you repeat the question?
The question was that this formula, this general formula, doesn't look real for general n. For n equals 2, it's clear that this is real, but well, it turns out to be real. Pardon? That's right. Yeah. Well, it is not obvious in this description, but if you think about this formula, I mean, this just takes out sign of E contribution for some specific modes where this is just equals to omega. So this, in the end, this is just sum over plus minus 1. So even after the regularization, you get a real number. So, right. But let me repeat what I said yesterday. It is very rare still that you can actually compute the Ada invariant. So for more general case, one way to treat it is to assume that this combined three-dimensional manifold, three-dimensional closed manifold W3, has even one higher dimensional manifold U4, such that W3 is a boundary of U4. In this case, yesterday I told you that there's something called Atiyah-Patodi-Zinger theorem, saying that eta is equal to the number of zero modes. I mean, more precisely, the index of D index of D slash on U plus integral over U of this standard A hat, trace exponential of f over 2 pi. And after the lecture yesterday, somebody asked what is this A hat. This is just a polynomial in terms of the curvature integral. So it has this expansion 1 minus 1/24th P1, where P1 is minus 1/4 trace R over 2 pi squared, where R is the space-time curvature. So if you know such a U4, then you can evaluate exponential of 2 pi I eta just by raising the entire thing over the exponential, because this integer part, which is not easily controllable, thankfully cancels in the exponent of exponential 2 pi I. So you get U. And because in this dimension, it's the only term which arises is this. So this is 24, 1/2, trace R over 2 pi squared So this is the formula. I mean, here I'm not including any U1 gauge field except for this discrete Zn background. So this is what you get. But so this is how would you would evaluate it if there is such a U4 available. Right. But it is not always the case that there is such a U4. So let's discuss what happens in those cases. So let's consider the following situation. Let's consider the following situations. So in the original 2D, you have one left-moving Majorana vial fermion, and also one right-moving Majorana vial fermion, right? But you also introduce Z2 symmetry, under which you say, let's say this is neutral, but this is charged under this Z2, right? So let's consider this situation. Before getting further, I should say that this part is known as the anomaly polynomial of governing the anomaly of the original two-dimensional theory. So, well, the computation of the anomaly polynomial is just the same on both sides, except for the sign, overall sign distinguishing left mover and the right mover. So let's say this minus 1/12, so 24th, 1/2, trace of r, 2 pi r squared. Then this side would have plus 1/12, the same thing. So of course, if you sum over the two, the anomaly polynomial is 0, right? Therefore, if you consider the Ada invariant governing the anomaly of this system on a three-dimensional manifold, for which you can find such a U4 whose boundary is W3, this Ada invariant is automatically 1 because this part is 0, right? However, you can easily find a situation where the Ada invariant is non-zero. So the example is that you just take W3 to be S3 over Z2 such that non-trivial Z2 background around pi 1 S3 over Z2, which is Z2, right? In this case, the combined eta invariant governing the anomaly of this thing is the eta invariant of this thing times the eta invariant of that thing, right? And because we have opposite chirality, you need to take the difference. So, but we just computed exactly the eta invariant we need. For the neutral thing, you get this, right? But for the charged thing, you get this plus 1/16. Therefore, well, I was very careless about the overall sign, but the fact that they are different is still true. So in this situation, 2 pi I eta is exponential of 2 pi I say minus 1/16 minus 1/16, right? So this is exponential of 2 pi I minus 1/8. So this is non-trivial. So this tells you one mathematical thing to us and one physical thing for us. One mathematical thing we can learn from this is that there is no U4 for which the boundary is of this form, S3 over Z2, together with a non-trivial Z2 bundle. You cannot extend the space-time and the Z2 bundle at the same time to the bulk. Yes?
Is this the analog of the similar example that we had yesterday, just a circle with RR or Ramon or Lewis-Schwartz boundary condition?
Right. So the question was, is it an analog of the circle with a Ramon boundary condition? Yes, this is the analog. Yes. Right. So the physical thing we learned is that this system of left moving Majorana fermion and right moving Majorana fermion with this charge assignment under Z2 has an anomaly under Z2. So that's what you learn. So let's study this anomaly in a more general way, because we have just studied this Ada invariant only on one particular background, which is S3 over Z2, right? So in order to characterize the entire possibility of the anomalies, you need to, in principle, evaluate this Ada invariant for all possible 3 manifolds with Z2 background, which seems to be extremely hard. But this is, in fact, tractable using some mathematical results. So Max Metlitsky seems to have talked about this, but let me just repeat. So let's assume that the anomaly polynomial vanishes, right? And suppose you can compute exponential 2 pi I eta for one 3D manifold together with Z2 bundle. And suppose you have a U4 such that this W3. So we just showed that there's no U4 for which W3 is the sole boundary, but you can find a U4 which might have a different boundary, right? So this can be disconnected, but you can call the totality to be W3 prime, and you can compute its Ada invariant. But now you can apply this APS index theorem to this setup, and you can conclude that these two are equal because the bulk contribution just vanishes because the anomaly polynomial vanishes. So this means the following. Yes, please. That's right. Yeah, therefore the orientation on this side, on the other side is different. Therefore, yeah. Thank you. The question was, how did I choose the orientation? And I chose the orientation here and there to be opposite. So the formal way of stating is the following. You can introduce an equivalence relation. So consider the set of 3D manifolds with Z2 bundle, right? And you divide it by the equivalence relation. This equivalence relation is such that, well, I guess I don't have to draw the same figure again, so I can just reuse this figure. So W3 and W3 prime is considered equivalent if there is a U4 connecting it. So that's the equivalence relation. And this thing is called I. And because we are considering fermions, I need to say that this is a spin manifold. So this object, this thing is called, denoted by this symbol, omega spin 3 of BZ2. And so we put the superscript spin because we are considering spin manifolds. And we have this 3 here because we are considering 3D manifolds. And we have this Z2 because we have Z2 bundle. So that's the explanation. And this is an abelian group where the addition is just that if you have W3 and W3 prime, the addition is just a disjoint union. So I just introduced a mathematical concept, but this fact shows that when the anomaly polynomial vanishes, when anomaly polynomial vanishes, the anomaly of 2D Z2 symmetric theory defines a map group homomorphism omega spin 3BZ2 to U1. So this is, so you just take a W3 together with Z2 bundle. So this omega is some absolute way, abstract way of writing this, denoting Z2 bundle. And to this, you just assign the partition function of the anomaly theory evaluated on this manifold, and this is a phase. So in the particular case of this Majorana fermion system, in this particular case, in this concrete case, what happened was that S3 over Z2 with non-trivial omega was mapped to exponential 2 pi I 1/8 by this anomaly of the fermion system. So you see that this element in this group has at least order 8, right? If you take 8 copies of it, this becomes 1. So that's trivial. But in fact, it's known that, this omega spin 3 BZ2 itself is Z8. So there's various ways to compute this. And again, when I first started learning this, it was very scary. But actually, this is something you can compute using the technique called Atiyah-Hirzebov spectral sequence. And again, it sounds scary, but you can learn how to use it. But anyway, for the purpose of this lecture, let's assume that we know this, because this appeared in Max Metlitsky's table, I guess. But now you know Yes, please.
The spectroscopers that you're referring to always converge at the finite page?
So there are various ways to, so the question is how to actually use this at the irreducible spectral sequence, and I'm not going to go into detail in this set of lectures, but let me just say that in this particular case, so in the general case it's very complicated, so I don't know the answer to your original question, but in this particular case it's kind of easy to show from this algebraic topology machinery that the order of this group is at most 8. So that's one algebraic topological info. But we already have a differential geometric info here saying that this object has order at least 8. Therefore, you already know from two different mathematical methods that this is at least 8, and at most 8, and this has at least 8. Therefore, this is exactly 8. So that's a good way to check that this is actually Z8. Yeah. Getting the fact that this is actually Z8 just from algebraic topology machinery is more complicated. But we are not algebraic topologists, right? We are allowed to use whatever subject of mathematics and also physics intuition to get this result. And this is Z8. Thank you for your question. So this means that in order to characterize the anomaly of a Z2 symmetric system in 2D, which depends on the spin structure, you just have to evaluate the anomaly theory on this one example, right? And you just have to check whether this is non-trivial or not. So that tells you when the theory is anomalous. For example, we learned that 8 copies of this system, so luckily I still have this system on the board, so what we learned is that if you just have a single copy of this system, it is anomalous under this Z2 symmetry. But if we have 8 copies, it's non-anomalous under Z2. So that's what we learned. So there is one string theory significance for this fact, which is related to the something called GSO projection. So I guess many of you studied string theory textbooks to some extent, and one popular way to do superstring theory is to consider some formalism called NSR formalism, and you learn a lot, right? And at some step, the textbooks start discussing some mysterious way of choosing spin structures on both sides and summing over them. And there are various choices, and somehow it's consistent, but you just don't understand what is going on. So that's the feeling I originally had. But this is directly relevant. So in this NSR string, in order to produce the physical superstring, you need to perform something called GSO projection. This is usually said that it's a sum over the left moving and the right moving spin structures, right? But you can always consider this right moving spin structure to be the product of the left moving structure times a Z2 gauge background. So sum over the both spin structures can be also thought of as summing over the diagonal spin structure together with the difference between the two, which is the Z2 gauge field. Therefore, this operation is consistent only if this Z2 symmetry is non-anomalous, right? And it so happens that the superstring critical dimension is 10, so that in the light cone gauge there are 8 pairs of Majorana-Weil fermions, which is exactly 8. So somehow things are consistent. So you learned originally the critical dimension of the superstring from a totally different computation, right? Of the vanishing of the conformal anomaly on the world sheet. But somehow it gives you the required number of fermions to perform the GSO projection. So I feel like we are encountering a kind of mathematical accident supporting the existence of superstring theory.
This would also say that 16 copies is okay.
Ah, yeah, that's right. But yeah, you're right. But still, it's still a bit non-trivial, right? We had a 1 in 8 case possibilities of failing, but I don't know. Right. And of course, people knew about this fact when they performed the GSO projection in the first place, because the same anomaly can be seen in a more traditional way, right? This is a somewhat modern or artificial way of seeing the same anomaly. And there's a different way of seeing the same anomaly. So the way you proceed is as follows. So this is side remark, note. So it's traditionally the same anomaly is viewed in a different way. So you consider 2D left moving, right moving Majorana-Weil fermion, right? And you couple Z2 just on one side. So you can put it on a cylinder, and you can consider non-trivial spin structure so that this has R sector, and this is into NS sector, right? So of course, in the R sector, Majorana-Weil fermion, well, formally has L0 being 1/12 to 24th, and L0 bar would have 1/80, so 48, and there's a difference by 1/16. So L0 minus L0 bar is 1/16. So this is scary because if you have a cylinder like this, and because we are in a spin theory, 2 pi rotation is not really a trivial operation, but a 4 pi rotation should be trivial, right? If non-anomalous. But the fact that L0 minus L0 bar is 1/16 means that 4 pi rotation in fact gives exponential of 2 pi I 1/8. But again, if you have 8 copies, this becomes 1. So there's no anomaly. So how do we reconcile this way of viewing the anomaly and that way of viewing the anomaly? So in fact, it's not too difficult. What happens is that this type of operation corresponds to different 3D manifold. So you have a 2 torus, right, with RNS structure, and you consider so this is a 2-dimensional manifold, right? And you consider one additional S1, but you don't consider just a trivial product of this 2 torus and S1, but you want to perform this 4 pi rotation, right? So what you do is that when you consider this, but when you glue the original point and the last point, so when you glue the end point and the starting point, you glue them by this 4 pi rotation, which is a t transformation t squared in SL2Z, acting on this torus. And you just have to evaluate Ada invariant in this manifold as before. And if you carefully reflect on exactly the things what I've been talking about, it's kind of a tautology that the phase you see here is in fact the phase you see there. So this is exponential of 2 pi I1/8. So this just means that in this cobordism group, S3/Z2 with this non-trivial bundle is in fact the same element with this rather complicated manifold, which we obtain by having a T2 and rotate it around and glue this with this SL2Z transformation. So that's how to reconcile the old way and the new way of understanding the anomaly polynomial. The anomaly of the GSO projection. So this is a good point for you to ask questions if you have any, because I'm going to switch gears. Yes?
In this example, you computed on this lens space.
Right.
In general, is there a way for saying, like, choosing nice 3 manifolds that will give you generators in these groups, or do you just guess?
The question was how to get the correct generators of the Bordism groups, I guess. So here, I randomly chose the lens space S3/Z2, and it happened to be the generator. I don't know any, my answer is I don't know any general way of getting the generators, but the mathematicians have a lot of experiences. So yeah, they right. So for example, there's a paper from about a year ago where people computed the anomaly of 4D chiral fermions and the ZN gauge groups. And in those cases, again, you need to know the generators of the Bordism group in 5 dimensions. Luckily, there's a certain mathematician who had worked them out. So you could just use their result. But I don't know how to do that in a systematic way. And I don't have any physics intuition of how to get the generators. Thanks for the question. Any other questions? Yes, please.
In these cases where you can't extend your, say, in this case, 3-dimensional manifold to a 4-dimensional manifold, are the corresponding anomalies always global anomalies?
So the question was, when you cannot extend the 3D manifold to 4D manifold, is the corresponding anomaly a global anomaly? So I think that's the definition of the word in the modern sense. So I would call any anomaly captured by the anomaly polynomial, it's in some sense perturbative or local anomaly. And everything beyond that, which can be only seen in manifolds which doesn't bound, I call them the global anomalies. Yeah, thank you for the question. Any other questions? All right. So let me switch gears and discuss the Greensward mechanism. So that's the example 3 in the original table of contents I announced. So what I'm going to talk about is the result from 1984, so still from some time ago. But before getting there, let's start by a simple example. Consider a 2D periodic scalar theta is identified as theta is 2 pi, right? And the action is the 2D integral of, say, some coupling constant and partial mu theta. Nothing more than that. So you learned this system in many places. It appears in compactified string. And there you learn that there are 2 U1 symmetries in this system, which is usually called momentum, along this direction, and also the winding number, which measures how many times our string wraps around this periodic scalar. So we can introduce background U1 gauge fields. So let's introduce background U1 gauge fields, A mu. This one is for momentum. And this one is for the winding number. So a mom and a win. So how do they enter the Lagrangian? It's not too difficult to figure out. It's not too difficult to figure out. Now, the action depends on 2 U1 gauge fields. Yeah, my mom and win looks almost the same. I'm sorry about that. Maybe I should have used different letters. And suddenly I'm going to the differential form notation, and somehow I was using yellow chalks, and let me come back to I'm sorry, wedge a win over 2 pi. So this is the way it appears in the Lagrangian. But now you should be scared, right? If you have a look here, there's a direct product of 2 U1 gauge fields. So this is clearly not gauge invariant. So under the gauge variation, where this winding number,
Could you just
yes.
tell me for sure which one is a mom and which
I'm so sorry. Let's just use B for the winding number. Right. B. Right? So this is supposed to be B. And then this is mean. This is totally wrong. I'm so sorry. Yeah. This is B. Then this is B. Yeah. But now I need to translate between my lecture notes and what I write in the blackboards. But let's say you do a gauge transformation for the winding number gauge field, and then this transforms, and delta of d theta plus a with b over 2 pi is, d theta plus a with d chi over 2 pi, right? And you try to partially integrate, and this is basically f with chi over 2 pi, and this is not 0. This is not 0, right? On a two-dimensional space-time. So this is bad. But you can cure this problem by adding a bulk term. But you have W2, and we introduce U3, and sorry, this is supposed to be W3 to be consistent with the notation so far. Then I include the term W3, and where we introduce f with b over 2 pi.
So f is dA. F is dA.
F is dA, right. Yeah, I need to, because, right. I need to decide what I would call, yeah, I'm sorry, F is dA. Thank you. So this is dA. Yeah, let me just use dA. Right, and you can see that if you do the gauge transformation for B here, gauge variation here is W3 dA with d chi over 2 pi, and because of this relation, this is y2 and dA chi over 2 pi, and this exactly cancels that. So this is the anomaly theory, and furthermore, you can represent this anomaly in terms of anomaly polynomial, because as you can clearly see, if it happens that W3 itself is closed, and if you can find the U4, then the integral over W3 of dA, let me just write it as d2 pi over dA and with b over 2 pi is up to some sign, 2 pi over U4 of dA over 2 pi with dB over 2 pi. So this characterizes the anomaly, mixed anomaly between the winding number symmetry and momentum number U1 symmetry. So I still have about 10 minutes, I guess. Yes.
Can you put the little quotes on dA and dB, or are you just reminding us that they may not be globally exact?
That's right.
Or globally well-defined?
That's right. Yes. Yeah. So the question was why I was putting those quotes, and the quotes was supposed to remind you that it's A and B are not guaranteed to exist globally. Yeah. Otherwise, they tend to vanish. The integral tends to vanish. So, pardon? I just wanted to say that A is not locally globally well defined as a one form.
But dA is well.
dA is well defined.
So why did you put quotations?
Well, but I cannot even write this way, right? Because this would mean that something not well-defined has a well-defined operation of D. So it's very tricky.
If you called the field strength of A F and the field strength of B G, then you could just write F and G.
That's right. That's right. Yeah. But I mean, there was a reason why I didn't use B in the first place, because for string theories, B would usually stand for two forms, right? But my handwriting is to be blamed, you know. If I could have distinguished momentum and winding more clearly, there should haven't been any problem. So there's a natural generalizations. I mean, this can be generalized easily. For example, in 4D Maxwell case, I will be kind of quick. So you start from f squared, where f is dA. So let me put the quotes around here so that nobody complains. Right? And just as before, you can introduce two form fields, locally two form fields, B and C, such that S, B and C has this form, 2e squared dA plus B squared plus I 2 pi, let's say dA plus B wedge C, right? I mean, everything is completely parallel to what I have done in the case of periodic scalar in one dimensions. Yes, please.
Before you move on, so
yes.
what happens at the self-dual radius? Is there something interesting going on?
Oh.
Because two U1s, we know that.
That's an interesting question. I haven't thought about that.
Can you repeat the question?
The question was, what happens at the self-dual radius where both U1s enhances to SU2? That's a good question. I don't know the answer. Yeah, let's think about that. Yes, because this doesn't generalize. Yeah, I'm confused. That's a good question. So, yes, please.
So this thing can be written as U1 left and U1 right.
Ah, you're right. Thank you very much. So Nati answered for me. So the answer is that the U1 momentum and U1 winding number is a linear combination of the left moving U1 and right moving U1. So in that basis, this is left moving U1 squared minus right moving U1 squared. And when at the self-dual radius, SU2 is just an enhancement from that U1. So the anomaly polynomial is just a trace SU2 squared and it's minus SU2 squared. Yes, that's surely the answer. Thank you very much. Yeah, it's always nice to have an expert in the audience, right? Right. So coming back to this discussion of 4D Maxwell, because of this term, there is a mixed anomaly. So the way to cure the problem is to add the bulk term where the bulk term is C dB over 2 pi. And just as before, when W5 itself is a boundary, this thing can be further rewritten as integral over u6 of 2 pi times dc over 2 pi with db over 2 pi. So it's completely the same. So let me summarize. I have only 5 minutes left, so let me just, yes?
Is it worth saying that these are now higher forms?
Yes, I'm going to say that. Thank you for point. So I'm going to say that these backgrounds are for the higher form symmetry. So in the case of periodic scalar, we considered first locally a one form, a mu, but this is not really a one form globally speaking, right? And then, so this can be said as one form U1 gauge field for which dA over 2 pi integrates to Z. And the thing we introduced there is two-form U1 field, U1 gauge field, and it would have a quantized integral. So this one-form U1 gauge field is for U1 symmetry. So you need to come up with some name for which this two-form gauge field is a symmetry of. So this is now called a one-form symmetry, one-form U1 symmetry. So by extension, this original U1 symmetry we are familiar with is now called zero-form U1 symmetry. And similarly, we can go further. You can also consider two-form U1 symmetry. Then you can introduce correspondingly three-form U1 gauge field C mu nu rho, so that dc integrated over some 3 cycle is integrally quantized. So that's what happens. So very generally, I'm going to wrap up. So in some sense, the ultimate generalization is to consider this Lagrangian in capital D dimensions of a p-form field coupled to source fields in this way, plus I over 2 pi y, which is now q plus 1 form field, with dp p plus x p plus 1. But in order for this product to make sense, you need to have D, capital D, space-time dimension, should be equal to p plus q plus 2. Right? And then it has an anomaly. So anomaly polynomial, which is 2 pi I time u capital D plus 2 of this d p plus 1 over 2 pi with dy q plus 1 over 2 pi. So you now see that this capital X is a background field for P-form U1 symmetry, and this Y similarly is a background field for Q-form U1 symmetry. So this is all very simple once you understand it. And what is surprising to me is that we encountered, we as a community of physicists encountered this structure first in this Greensward mechanism, which was used in a rather ingenious way. So what's the significance? String. So sorry for going over time, but you consider E8 times E8 heterotic string or supergravity, right? It has lots of fermions. And it has an anomaly, an anomaly polynomial of the fermions has this form 2 pi I. And because this is a 10-dimensional theory, anomaly polynomials are integral over the 12-dimensional space, and it has this form, instanton number of first E8 plus instanton number of the second E8 minus P1 of the metric, which I just introduced, divided by 2 times, so this part is 4 form, and let me just write Z8 here, because I don't want to be specific. It has a ugly form. So this is the anomaly polynomial of fermion. So you say, oh, it's anomalous, right? How can you have an anomalous theory, anomalous matter content, when you want to perform the path integral? So the good thing is that the heterotic string has a B field, which is a 2-form field, which, as I discussed, has this mixed anomaly between the 2-form symmetry and 6-form symmetry. So this has anomaly polynomial of the form 2 pi I U12 dx3 over 2 pi with d by 7 over 2 pi, right? So by declaring that somehow this background field for the 2-form symmetry equals this part. Sorry for writing it interchanged, but this part, you try to identify this part, and then you identify the other part, and you can make it cancel. So that's how 10-dimensional heterotic string or heterotic supergravity has the anomaly cancellation. So it's kind of amazing to me that this mechanism was first encountered in this complicated form. So that's one reason I think the Greensward mechanism was and still is kind of hard to understand if you follow the standard textbook on superstring theory. But from this modern point of view, you know that, fermion has an anomaly, and this B field also has an anomaly, and you just choose them to cancel this factorized form of the anomaly. And that's it. So that's it for today. So thank you very much.
All right, if not, don't forget tonight is a public lecture at 7:30, and we're done, right?
Yes,
We're done.
you're done.
We're done. Okay, yeah, we're done for the day, so see you at the public lecture at 7:30.